Hi again, everyone. Tom McNamara back, talking about exponential functions. In this video, I thought I would do one or two kind of applied problems from my math lab for you to help you get a feel for what these are about. So this problem reads, find C so that f of x equals c times a to the x models the situation described. Okay, so we're going to have a scenario given to us that we can use an exponential function to model. And it says there are initially 5,500 bacteria, so we could pretend we have some sample in a petri dish, and the sample doubles in size every hour. Okay, so let me switch to the document camera here. Okay, so initially, 5,500 bacteria. And now here's what our function is going to do. It's going to take an input value, which will be a time in this case, and then we're going to have some kind of rule for measuring the output variable, which is going to be the number of bacteria in the petri dish. Okay, and that's what we want to come up with. Now, they tell us in the problem that the starting number of bacteria is 5,500, and then it doubles in size every hour. Okay, so after 2 hours, we double 5,500, getting 11,000. Sorry, after 1 hour, that happens. After 1 hour, we double, and we have 11,000. After 2 hours, we double that, and we have 22,000. At the third hour, we double what we had at the beginning of the hour, and we're at 44,000. Okay? Now, all that can be related back to the base amount, the starting amount. Okay, so instead of thinking of this as 11,000 times 2 to get the 22,000 at the end of 2 hours, what I recall is that this is, okay, the 11,000 is 5,500 times 2. So at the end of 2 hours, it's really 5,500 times 2 squared. Okay, you multiply by 2 and then you multiply by 2 again. And then for the third hour, you multiply by 2 3 times. So here's my function. F of x equals 5,500. So your starting amount always goes out front. The base of your exponential is determined by what's happening for every unit of time. And in this problem, they said the sample doubles in size every hour. Okay? So it makes sense that we're using exponential function base 2 in this scenario. Okay? So let's go back to the statement of the problem and see what they're asking us here. So what do they want for C? Well, C is 5,500, your starting amount. We'll check the answer. Great. What is A? A is 2. The base of our exponential function is 2 because the bacteria were doubling every hour. Okay. What does the variable x represent? Well, the input to the function, if we look back here, the function is supposed to take a value of time, take a time, and tell us how many bacteria. So the input, remember the input is x, it's a multiple choice question, time in hours. And then the output, what does the output represent? They didn't ask us. Okay. Okay, we just went to the next one. But if they did ask us, what does the output represent? Well, the output represents the count of bacteria. Okay, somewhat similar problem here. Okay, so we want another exponential function that models this scenario. So in 2000, a house was worth $220,000. and the value decreases by 12% every year. Okay, the value is dropping. And they want us to write an exponential function that gives the value of the house. Let me switch to the document camera here. So, once again, we're looking to make a rule here. The input is going to be time. How many years have you had this house? And the output is going to be the value of the house in dollars. Okay, the value of the house in dollars. So, the best way to think about a problem like this is don't do a subtraction, okay? It may be natural to start out that way, start out thinking that way, saying, okay, well, you should find 12% of the $2,200,000 and then subtract that, okay? Think about what you have left. If you lose 12%, then you have 88% of what you initially had, okay? 88%, now we can find 88% in a single multiplication. And you're going to do that every year. Every year you have 88% left of what you had at the start of the year. Okay, so here our function f of x, the starting value of the house is $220,000, 0.88 power x. Okay, after 1 year we have 88% of the starting value. After another year we have 88% of the value that we had at the beginning of that year. So we do 88% twice, and then we keep on going that way. Okay, let's switch back. Okay, so what is C? 220,000. Okay, remember C is always the starting amount in these functions. A is determined by how the output is changing. In the previous example, the output was doubling every hour, so A was 2, because we're doubling it. Here, 0.88, because we had 88% of what we started with every year. We were losing 12%, which means we have 88% left. Okay, and the variable x, well, it's kind of lame that it's the first one every time. I hope that doesn't always be the case, but x is time, okay? The starting year is 2000. So if you're trying to find the value of the house today, it's 2022, you'd put in 22, okay? So these are some example questions to get us working with exponential functions. So they're great for modeling scenarios where you have a percentage increase or a percentage decrease. That first one we were working on, you might say, well, that wasn't a percentage increase, but in a way it is. It's a 100% increase. You're doubling the size, okay? So exponential functions are really useful for percentage increase, percentage decrease scenarios. So they're great for modeling population, modeling financial scenarios where you're earning interest or the value of something is dropping, as in the case of the house, okay? So the base of your exponential function is based on the percentage increase or decrease that you're experiencing.